Hi there, welcome to this lecture series on matrix algebra. This is lecture 35. The topic is linear system of ODEs. This is part 2 of this lecture, and then in this part we'll continue our discussion on applying matrix exponentials to linear systems of ODEs. Let's get started. Let's do a very quick review of the powers of a diagonal matrix. So given a diagonal matrix D with the diagonals, and then D to the power K is also a diagonal matrix with the powers of the original diagonals on the diagonal. And using that, we can find the exponential of a diagonal matrix by using the Taylor formula. So e to the d, and treating d just as the exponent of this exponential function, and then this can be written as a Taylor series. We assume that it can be, and then it's 1 over k factorial times d to the k. And then d to the k, we can put in this expression, which we showed in the previous slide. And then we can move the summation sign into the every term. And since everything else is 0, then we just need to put the summation sign on the diagonal. And then on each diagonal, we just have 1 over k factorial and lambda with certain index to the power k, summing over that. And we see that is the exponential function of lambda 1 and then of lambda 2 and so on. And then the general exponential function for a matrix that's more general, n by n a, will be the following. So we still have a condition here that the matrix A can be diagonalized. So A can be written as P times D times P inverse. And then you can use that to write the A to the power K. Then this will be P times D to the power K times P inverse. So all this we have seen already several times in the previous lectures. And then using this, we can write out the exponential of the matrix A. And by the Taylor series, it's the summation of this Taylor series expression. And then where we have AK, we put in this expression here. And then we can take all the terms that don't have anything to do with index outside the summation sign. So we pull the P on the left out, and we put P inverse on the right out, and then whatever stays in the middle, we sum them over K. And then we see that this expression here is exactly the exponential of the diagonal D. And we can put it in. It is e to the lambda 1, e to the lambda 2, and so on the diagonal, and 0 otherwise. So that will be the expression for e to the power a. And then to compute this as a function with t in it, we want to compute e to the td and e to the ta. We can quickly review that. If D is a diagonal matrix, and then scalar multiple TD is also diagonal, I'll just have that on the diagonal. And then when you compute the exponential of it, you will just have exponential of T lambda I on the diagonal. So this will be T e to the T lambda 1, e to the T lambda 2, and so on. And similarly for a general matrix A, which can be written like this, and then we will have T times A would be P times T times D, because T is a scalar number. We can multiply it on D first and times T inverse, and then T times D will be just this matrix here. And then we can compute e to the TA by just simply writing TD instead of e to the d here. Now let's go back to the population model, where we have a model, the growth of two competing populations, simultaneous growth. In the previous lecture, we set up the system like this with the initial condition, and we know that the solution is e to the ta times initial condition. So we want to compute e to the ta. Then we need to diagonalize the matrix A, which is the coefficient matrix for the model here. Then we need to go through the computation of eigenvalue and eigenvectors. If we carry out that, we'll have two eigenvalues, 1 and 4, and two corresponding eigenvectors, v1, v2. So with these informations, we can form the P matrix, which is collecting the two eigenvectors. I have that. And then I know that P inverse times A times P will be a diagonal matrix with the eigenvalues on the diagonal, and putting the value, it will be 1 and 4. So to be specific, let's collect all we need. So we have the P matrix here, and then we can compute the P inverse, and then we write it here, and the diagonal matrix is 1, 4. And let's compute T times D, which is just D multiplied by T, so we get this matrix. And then e to the TD will be just making the diagonal terms the exponential functions. And then we can use all this information to compute e to the TA, which we derived earlier. It will be P times e to the TD times P inverse. And then all the information is listed here. Let's put it in. And this is the P, and then this is the e to the TD, and this one together with 1/3 is P inverse. So we have a scalar number and the three matrices. And one can carry out this multiplication. Here are very simple numbers. And if you carry it out, and you get this matrix e to the TA. So we'll have 1/3, and we'll have these 4 entries of that matrix. So finally, we can put this back into the solution. So the solution for the population x1 and x2 as a function of time t will be this matrix here, which is e to the ta times the initial condition, that's x1 bar and x2 bar. Now, just for the sake of verification, let's write out the solution. So the solution is this one, and we want to check that each component, the x1 and the x2, they would satisfy the system of the ODEs, which is this is the ODE and this is the initial condition. Let's verify the initial condition first. That is, you put t to be 0, you will get x1 bar and x2 bar. So if I put t to be 0 in this expression, then e to the 0 is 1. So you just get 1 for wherever you have e to the something t, then we get that. And we see that that's 0, and this is 3, and this is 3. Multiplied by 1/3, you get the identity matrix, so you just get x1 bar, x2 bar, which is the initial condition. So the initial condition is satisfied. And next, we can verify the ODEs. So let's see that xt here, we will have it as e to the t times a times x bar. We can put in the exponential of a, which is p times e to the td p inverse, and where this is the diagonal, and then e to the td is this diagonal matrix. Then we can compute the derivative d over dt of this exponential term, because note that in this solution here, everything is constant except this e to the td, which is a function of t. The others are constant in time. Okay? So the derivative, if we differentiate it's only this term that will contribute to the differentiation. Okay, so if we differentiate that, and then we see we need to differentiate each diagonal, and then we'll get e to the t, and for this we'll get 4 times e to the 4t. And then we see that this is the same as writing in this form. I can write e to the t, e to the 4t, and I can write this diagonal matrix with 1 and 4 on the diagonal, and this product will exactly be that matrix. That can be easily verified, and which means that this is the D matrix times this is e to the td. Okay, therefore we can compute the derivative of t and xt in dt. So put it in the x, is this expression, that's our solution, and then differentiate in this one alone because all the others are constant, and then this one gives me d times e to the td. We put it in there, and then finally we're gonna right here we're gonna squeeze in an identity matrix in the form of P inverse times P, because this is an identity and it will not change the result. It's like multiply by 1. And then I'm going to group the first 3 matrices together and group these last and the second 3 together. And I notice that this one is just A, and then this matrix here is just e to the ta. So I have this expression, and then I see that that's exactly a times x of t, because e ta x bar is just x of t, because that is our solution. Okay, so we verified that this expression also satisfies the differential equation, plus it also satisfies the initial data, therefore it is the solution. Now we have reached the end of this lecture. In the next lecture, we will still be talking about the topic of ODEs and some more related discussions. So I hope you enjoyed this lecture, and I'll see you next time.